In this paper, we have brought the edit distance calculations into the homomorphic domain. We have developed a completely new algorithm, and we call this Leuvenstein. And this is a joint work together with Jan-Pieter, Bojan, Nam-Luc, and Ingrid, and I'm Wouter, Legiest. In this presentation, we'll first give a short overview of TFHE, edit distance as well. Then we're going to discuss how we brought actually the edit distance into the homomorphic domain. And we'll end our presentation with our results and our conclusions. But first things first, what is our homomorphic encryption scheme that we have used? We have chosen to use TFHE. TFHE is a Boolean branch FHE scheme that makes it possible to encrypt small integers into an individual ciphertext. So for instance, you can choose 4 bits of plaintext space and you encrypt that into an individual ciphertext. We have chosen the 4-bit model because it gives us the perfect trade-off between the size of the plaintext space and also the size of our lookup table and the complexity to calculate it. One of the properties that TFHE has as well is lookup table evaluation. During programmable bootstrapping, we can actually choose a lookup table of 16 elements ourselves that can be evaluated during the bootstrap. This gives us the possibility to do any arbitrary functions in TFHE. Because of the mathematics of the TFHE scheme, it's actually possible to not only have a 16-element LUT, but actually have a 32-element LUT. One of the downsides is that these upper 16 elements we cannot freely choose ourselves. These are actually defined because of the negacyclic properties of TFHE-RS, and they're defined by how we choose our first 16 elements in our LUT. So this is the TFHE scheme that we used in our paper, but we brought it to the edit distance. But now, what is an edit distance? We'll start from the bottom. Edit distance is a way for a computer to express how similar strings are. And we actually want the scoring that if we give a computer 2 strings, we want to have a scoring that says low when the 2 strings are very similar, and when it says high when they're very dissimilar. This is actually the basis for DNA matching, name matching, and for PDF processing, namely OCR correction. But the most straightforward way for a computer to check if 2 strings are equal is actually by just checking all of the corresponding characters. This is what is called the Hamming distance. But one of the downsides that you can now already clearly see in our example is that we have 2 strings that are super similar. We as humans see directly, oh, there is only 1 character missing. But for a computer, if you're only going to check the corresponding characters, yeah, everything is wrong. So you get like an Hamming distance that is 6. And this is now what the edit distance prevents. The edit distance measures how many operations do we need to do to convert our first string into our second string. So you can clearly see, okay, our edit distance is only 1 because we just want to remove 1 single letter. The edit distance will count these operations. It will count the possible operations to convert the first string into the second string. And these operations are the deletion of a character, the insertion of a character, or the substitution of a character into another character. So in our first example, yeah, we clearly see we just need to delete the H. In our second example, we want to delete our H, but we also want to convert our E to an O at the end of the string. So the edit distance of the second example is only 2. While our third example, yeah, you clearly can see we want to do an additional substitution, so that has an edit distance of 3. As a human, we can fairly do this quite easily. But now, how are we going to put this into an algorithm? How are we going to calculate it? And this is where actually the Wagner-Fisher algorithm comes along. This algorithm will check the edit distance of each of the possible substrings, the comparing of each of the possible substrings of the 2 strings that we want to check, and we're going to put each of these individual outcomes into this gigantic matrix. So for instance, in our example, we have, if we want to take it more slowly, I want to convert our Sabathon into a Sabbath. We're first going to check that substring by the time. For instance, we can check our two substrings that we now have is sub against sap. Substrings are equal, so the added distance that the outcome is also 0. We're going to continue by extending these substrings a bit by bit. So further in the algorithm, we want to check Saba against SAP with the double B. You see here we need to do one operation. So our added distance between these two substrings is becoming a 1. And this is now done for each of the possible substrings in our input words to build up this whole matrix. So the actual added distance between Sabaton and Sabat is 3. Now, how are we going to calculate this? This is done by a mathematical equation that every cell is the minimum of 3 previous cells. So we need our 3 previous outcomes to calculate a new cell. Besides that, in our cell definition, we also need to calculate the equality of the characters that we're checking. So first we need to check this equality, and then we can define, okay, it's the previous, or we need to calculate this min. Sadly enough, in the FHE space, of course, we need to calculate everything. So per cell that we need to calculate the min function, and we need to calculate the equality. As well, for the last 50 years, there have been more improved algorithms to this Wagner-Fisher algorithm, and one of these algorithms is actually the Myers algorithm. This is an improved way to calculate it. It's made more efficient. And one of the bases of this algorithm is that it checks that each of the adjacent cells only have a difference of maximum a -1, a 0, or a 1. So instead of storing our complete matrix, we actually can store only the differences between each matrix. So we only need to store like a 1, a 0, or a -1. And the same information is being kept. So we have altered our cell definition a little bit more. So first, we now have an additional definition of our delta V and delta H values. And we can now insert these into our larger cell formula for cell definition. We first get a new definition, and we can convert our algorithms completely into our a V-out and an H-out formula. These, in essence, still calculates the same as a couple of slides ago. But we now want to evaluate these functions into the homomorphic domain. For the people that can quickly do mathematics can clearly see this does not fit. Our delta H, our delta V values have 3 possible outcomes. Our equality has 2 possible outcomes. So in total, we have an 18-value input space, but we only can map that to a 16-element LUT. So this does not work very well. What we have done in our paper is we have converted these algorithms, these formulas, into this form, just by doing some simple mathematics. But this form actually gives us the possibility to express this in this lookup table. This lookup table makes it possible for us to do an 18-input LUT by only using 16 places. And this is because we have converted our formula into a form that has 2 zeros at the beginning of our table, but also have 2 zeros at the ending of our LUT. So this state that our first 16 elements we can just freely choose, we can put that into our LUT, but the 16 following outputs that you get from the negacyclic property follow the correct output of our function. So now we made it possible to do a complete cell calculation into one single PBS. So we still need to calculate the whole matrix, but we now can do it with one single PBS. Besides that, we also, besides this efficient way to calculate each of the individual cells, we also have found a better way to do the equality checking in our algorithm. So for instance, consider the case where we have ASCII encoding characters. ASCII are 7-bit characters, and those we are going to store into 2 ciphertexts. The first ciphertext will take the lowest 4-bit of the ASCII character, and the uppermost 3-bit are stored into a second ciphertext. So if we now want to check two characters against each other, each character has two ciphertext, we're just going to subtract the corresponding characters. What we now know is that if in this lowest part, if there is a 0, we know that that chunk of our characters is equal. So, but we want to check that first. So we're going to put that into a PBS, and that PBS will output a 0 if it's correct, a 1 if it's not correct, if they're not equal. And we're going to put that output in the highest bit of our most significant chunk. So if we now add these to each other, we know that in this ciphertext, if this ciphertext contains a 0, we know that our complete characters are equal. If this does not contain, a 0, we know it's everything else and they're not equal. So we need to have an additional PBS as well to then check if our characters are equal. But by now using two PBSs, we can check if ASCII encoded characters are equal or not. But now, how does this compare to the theoretical side of things? Is if we're going to look at the cell calculations in a straightforward Wagner-Fisher implementation, this would take 94 PBSs. We can reduce that to a single PBS. For the equality checking, a typical equality checking would take 5 PBSs. We can reduce that to 2 PBSs. So in total, we can have a reduction of our PBS calculations per cell by a factor 33. We can reduce it from 99 down to 3. This is per cell. We still need to calculate every cell of our matrix, but we can already have a reduction of this. We also did some tests with it. We put it in code as well, and we checked it against a known implementation of the Zama compiler. So the Zama compiler takes a high-level Python input, you just give it to the compiler, and then the compiler calculates the FHE program. We have tested it for 3 different cases, and you can see that for our 8-length characters, the Zama compiler roughly takes 240 seconds, while for the case of when our characters are 256 long, it takes roughly a week to calculate that. We can reduce that week down to only 35 minutes. So that's a reduction of a factor roughly 280x. If we then compare it to our 8-length characters, we can reduce our 240 seconds down to 2.3 seconds. So while we see that there is still a need for manual conversions of all of these algorithms down to the FHE domain, we can beat an existing compiler by a factor 284. So there is still a need to manually go through these algorithms and find the most optimal way. Besides that, in our paper, we have discussed a bit more about how we can skip certain parts of the matrix, how we can do the noise analysis, how we can compare unencrypted to encrypted, but therefore I happily point you to our paper. So thank you for your attention, and hopefully you learned something. Thank you.